Hello, this is Noson Yanofsky, and we're studying discrete structures. That's the class. We're going to do today section 3.3 and section 11.3. They're connected. They're both short sections, so we put them together as one. We're going to talk about matrices, adding matrices, subtracting matrices, scalar multiplication of matrices. We're going to do lots of different matrices. And then we're going to skip to section 11.3, which talks about multiplication of matrices. But that's a little bit far away. Let's talk about it. So matrices are arrays. We're computer scientists, so we know about arrays where they're just two-dimensional arrays. That's it. Okay, and they have numbers. They're arrays of numbers, usually real numbers, and they have. These are. It took me a long time to get it straight. These are rows. Okay, and these are columns. Okay, so you have to get this. So this is the first row, second row, mth row. Okay, first column, second row, column, nth column. Okay, and each element in the array is you can describe each element in the array. Okay, so this has. These are subscripts. They describe the elements. So 1 means first row, first column, first row, second column, first row, nth column, second row, first column, second row, second column, etc., etc. Okay, and so we call this an M, that's the number of rows, by n matrix. Okay, and we write it like this, and we say it's an M by n matrix. We always put the number of rows first and the number of columns second. Okay, great. Here's a typical example of this, and then we write it as follows. We say the Aij position. So if this matrix is called A, we talk about the Aij position. For example, in this matrix, this is, let's go through this. This is a 1, 2, 3, 4 by 1, 2, 3. This is a 4 by 3 matrix. Okay, and we're going to talk about different things. So for example, the A1, 2 position is the first row, second column, and that's a 12, because that's 12. Okay, and the A2, comma 1, that's the second row, first column, second row, first column, that's a 78. Okay, so that's the way we do these things. Okay, and finally, A3, comma 2, let's see what that is. 1, 2, 3, comma 2 is minus 68. Minus 6.8. 6.8. 6.8. Okay, so these are positive or negative real numbers. Great. So that's what a matrix is. Okay, and we're going to talk about. Great, so we talk about matrices. This is just like we always do. We introduce a concept, and then we talk about operations on the concept. So we're going to do this again over here. Okay, just in order to get this operations on the concept, I just want to keep the following notation. We're going to do the following. This m comma n equals, this is the way we're going to describe the set of m by n matrices. Okay, so we're going to talk about this set of m by n matrices, and we're going to talk about different operations that one can do with matrices. Matrices show up all over. In a sense, just to give you the feel of it, matrices are just giant numbers. They're not giant numbers, but they're a generalization of the concept of numbers. In fact, a 1 by 1 matrix with just the number A11, with the real number in it, that's a number. Okay? So numbers are special types of numbers. I'm sorry, numbers are special types of matrices. But matrices are vastly more important. They show up every single part of computer science, physics, mathematics, all over. Okay? They are used all over, and they are fundamental for us. Great. Let's start talking about some of the operations that we're going to have for matrices. Again, this is probably the easiest section that they have. So one operation is as follows. The transpose operation. Okay, and what that does is matrix A goes to a transpose. Okay, and I'm going to show you an example and then prove it, then show you what it is. But basically, what it is you take an M by N matrix, okay, and you turn it into, this is the transpose, on, oops, didn't do that right, an N by M matrix. You take an M by N matrix and you turn it into an N by M matrix. And let me just show you how it works. If you have the matrix B, which is equal to 3, 6, 7, 0, 4, 2, okay, then B, here's the way you write it, B with a T on top, capital T on top, T for the word transpose, is equal to, notice this is a 3 by 2 matrix, so you're going to have a 2 by 3 matrix, okay, and the 2 by 3 matrix is 3, 7, 4, 6, 0, 2. Okay, and basically what you do is you turn it on its side, but you turn it on its side very carefully. The 1, 2 position becomes the 2, 1 position. The 2, 2 position, second row, second column, is the 2, 2 position, second row, second column. The 3, 1 position becomes the 1, 3 position. Third row, first column becomes first row, third column. Okay, let's be formal with the way we write it. We say as follows: A transpose, the ij position, okay, what's that equal to? Let's go through that again. A is a matrix. A transpose is another matrix. The ij position of the A transpose is equal to A of j, I. Turn it around. Transpose it. Flip it. Okay? So that takes, that's a simple operation. Okay? Actually, all the operations are pretty damn simple. So let's do the next one. The next operation is addition. You know what? I want to write up on top. I like writing on top. So, okay. The next operation is addition. Okay, and it's the world's simplest operation. Let me just show you what you do. First of all, what does it do? It takes an M by N matrix and pairs, this is ordered pairs, an M by N matrix, takes two matrices of the exact same size, and it outputs, okay, another matrix of the exact same size. Takes two matrices and of the same size and outputs the same size as that. Okay, let's do a simple example. If I have a matrix 3, 6, 0, 7, 4, 8, I'm making all the entries to be positive whole numbers or non-negative whole numbers, but they can be real numbers, they can be anything, they can even be complex numbers, doesn't matter. Okay, well, actually I'm allowing negative numbers here too. 9, minus 5, 18, 0, 4, minus 12. Okay, so this is a 3 by 2 matrix, this is a 3 by 2 matrix. They're the same size, therefore we can add them. That's addition, we can add them, and here's the way we add them. Simplest thing in the world. We're going to get out a 3 by 2 matrix and this is a 3 by 2 matrix, a 3 by 2 matrix. We're going to get out a 3 by 2 matrix, and basically what you do is you add them point by point. 3 plus 9 is 12. 6 plus minus 5 is 1. 0 plus 18 is 18. 7 plus 0 is 7. 4 plus 4 is 8. 8 plus minus 12 is minus 4. Okay, but I want to show you the form of this operation, and so it goes as follows. If you have a matrix A and you have a matrix B and you want to add them, you're going to get another matrix. Let me tell you what the ijth position of that other matrix. So again, if you have a matrix A and a matrix B and you add them, you want to look what the ij ij position of the a plus b. Answer, it's equal to, let me tell you what it's equal to. You look at the ij element of a, and then you add it, add as in real addition, these are real numbers, okay, to the b, I, comma j. Okay, just want to say, this, we're using one symbol, plus, plus. This is plus of real numbers, this is plus of matrices. Okay, we're using one symbol for two different operations. In computer science, it's called overloading. We're overloading that operation, but that doesn't bother us. We understand what's going on. Sounds good? Okay, so that's the second operation. Okay, great. Guess what? We're going to do another operation. Take a picture. Let's do another operation. Subtraction. Okay, which is minus. Again, it takes an m by n matrix and another m by n matrix, the same size, and outputs another m by n matrix. Okay, and the operation is as follows. I can do this because you don't have an eraser. You have to copy the notes. Subtraction, okay, and I'll show you how this works. Same thing as here. You subtract this from this. You subtract each one of the entries. Okay, so let's actually do this operation. Let's do it. 3 minus 9 is negative 6. 6 minus negative 5 is 11. 0 minus 18 is minus 18. 7 minus 0 is 7. 4 minus 4 is 0. 8 minus minus 12 is 20. Okay, so that's the subtracting operation. Works beautifully. Okay, let's do another one. So that's the subtraction. I'm sorry, that's the third operation, is subtraction. So you have to copy that over, and I'm going to make it another operation. The other operation is negation. So this is the fourth operation. The book has these two. I'm just going through it with you. Negation. Okay. And again, what this does is it takes an m by n matrix and outputs an m by n matrix. Let me just show you how it works. Not hard. Okay. Take the matrix, negate it. That means put a minus in front of it. It's equal to, you guessed it, minus 3, minus 6, minus 0 is 0, minus 7, minus 4, minus 8. For the hell of it, let's make this a minus 8, and this becomes a plus 8. Okay, so it negates each element. Not hard. Let's write it up in terms of formally how it's written. A is a matrix. Minus A is a new matrix. Okay, it's the negation of it. Okay, and it goes as follows. The ij position of minus A is equal to the same element before, just a minus in front of it. Okay, so let's just go through exactly what this means. It says as follows. A is a matrix, minus A is a matrix. This tells you what the ijth position of that, and what it is look at the ijth position of A, put a minus in front of it. Don't do anything else than that. Okay, fifth operation. Fifth operation, and then it's pretty simple after that. For this fifth operation, okay, it's called, this is the fifth operation, it's called scalar multiplication. Scalar multiplication. Scalar means a real number. Pretty much in this case it means a real number. Okay, so let's write it out. Let's do an example first. Take a matrix, A. Stop for a second. Take a matrix A. A is equal to 3, 6, 0, minus 7, 4, 8. Okay, great. Now take a real number. Okay, 5, that's a real number, times A, or dot A. This is scalar multiplication. Okay, is equal to 5 dot, and now we have the matrix. 3, 6, 0, minus 7, 4, 8. Sounds good. Okay, what's this equal to? Very simple. Just multiply each entry by 5. Multiply every entry of the matrix by 5. And so what you're going to get out is as follows. Same size matrix, exactly the same size. This is a 3 by 2. This is going to be a 3 by 2. And what you do is you multiply each entry. So 5 times 3 is 15. 5 times 6 is 30. 5 times 0 is 0. 5 times minus 7 is minus 35. 5 times 4 is 20. 5 times 8 is 40. We're finished. Let's be exact about it. That's a nice example, but let's be exact about the formal definition. Okay? Let C be a member of the real numbers. A member of, okay, an m by n matrix. Okay? A is some n by n matrix. Then C times A is a new matrix. Okay, great. Now you ask yourself, what is the ijth position of this new matrix? What's in the ijth position? So you say, what's in there in the ijth position? And the answer is very simple. Look at A, I, J. Look at the element in the ijth position and multiply it. Let's write multiplication like this by C. That's it. So again, this C dot A is a matrix. This A, here we're doing, this is a number multiplying by that. Okay, and it works exactly like this. Let's just see what this scalar multiplication is. You take a real number, cross an m by n matrix. Take any pair of these, and what you're going to get out is an m by n matrix. Okay, very nice. Okay, can't get much simpler than this. Okay, great. Let me just tell you a typical homework question, because I will not a homework question, a test question. Okay, now that we have these 5 operations, let's just go through them again. Addition, subtraction, transpose, scalar multiplication. Addition, subtraction, scalar multiplication. What was the last one? Let's try that again. Transpose, addition, subtraction, scalar multiplication. Oh, and negation. We have these 5 operations. So we can talk about different operations. We can talk about different things. I promise you on the test, on the midterm, on the final, there will be a matrix operation, something like this, a problem like this. I will give you matrices A, B, and C, and then I'll say, what is this equal to? Okay, and the way you do it is you have to do it as all math things from the inside out. So you have to figure out what A transpose is. Write that in a book, in a thing. You have to figure out what 3 times B is. This is scalar multiplication. Then you have to add them. That's going to take care of this. Then you put the transpose of that. That takes care of this. And this is minus or negation. CT, figure out what the C transpose is. Scalar, multiply it by 4 and subtract that. So you're going to have something like this. Not hard, it's basic bookkeeping. Okay, you have to just keep track of what you're doing, put it together. There's homework questions from it, there's the answers in the back of the book. You got to do it just to get it in your fingertips. Okay, you know how to multiply numbers, you know how to do that, you know how to add numbers, subtract numbers, etc., etc. It's just doing it point by point, so you have to do that. Okay, great. One other concept from this section. Okay, a graph can be represented by a matrix. Okay? A graph can be represented by a matrix. The best way to see it is this example. It is an example. Okay, so here's a graph with 1, 2, 3, 4, 5 points. Okay, and edges. Many edges going from here to there. Well, you can represent this graph by what's called an adjacency matrix. You think I know how to spell adjacency? A-D-G, adjacency matrix. Okay, and it goes as follows. Okay, let's see here. From 1 to 1, there's nothing. From 1 to 2, so nothing is 0. From 1 to 2, there are 2 maps. From 1 to 2, that's parallel. From 1 to 3, there's nothing. From 1 to 4, there's nothing. From 1 to 5, there's nothing. Okay? From 2, the only thing out is from 5 to 5. So from 2 to 5, there's 1. The rest are all zeros. Okay? Let's do this. From 3, here's the kicker, from 3 to 5, there are 3 maps. From 3 to 5, there are 3 maps. Okay? Everything else is 0. Okay? This one's interesting. From 4 to 4, there are 2 maps. Okay? Also, from 4 to 1, there's 1 map. Okay? And that's it. Okay? And 5, the only thing 5 has is 1 map from 5 to 4. The rest are all 0. Okay? So this perfectly describes this. If you want, we can call this matrix M for matrix. Then M, or let's call it M sub, so this is G for graph. Okay? And M sub G, in other words, the matrix that's described by G, so let's write it like that, M sub G. Question, what's in the ijth position of M sub G? How do you describe the elements? Well, it's equal to number of arrows. Technically, this is a digraph, directed graph. We talked about this. Number of arrows from vertex I to vertex J. Okay? And that gives you that. Great. Question. Okay, so that's very nice. Question. It brings matrices. We were talking about graphs, so matrices become very important. Question. What happens if M transpose is equal to M? What graph would that correspond to? Let's think about it. What that says is that M transpose of I comma J is the same thing as M of I comma J. That's exactly what it means. In other words, what does it mean for 2 matrices to be the same? All their entries are the same. Hey, what's this entry? We know how to write that. What is it when we transpose an entry? So that says that is Mj comma I. That's what the transpose is. Now, let's follow these equal signs. If Mij is the same as Mji, what does that mean? Well, what it means is that if you have a vertex I and you have a vertex j, and you have, let's say, 3 things from I to j, then if this is true, we call it if it's true, well, I'll tell you what it's called in a second. If you have 3 things from I to j, then you must have 3 things from j to I. Okay? Let's write this another way. We can write this another way as follows. Since all the arrows are both ways, you can write it as 1, 2, 3. Okay, so that is a, okay, and we call such a matrix that satisfies this symmetric. Symmetric, it goes both ways. Symmetry, there's a symmetry. There's a symmetry there. Whatever goes one way can also go the other way. One other point. Okay? If there are no parallel edges. Good Lord. What did we say parallel edges is? Means you have 2 points and you have more than one edge in between them. If you do not have parallel edges, then between any 2 points you either have 0, nothing there, or 1 there. Then M of G, given a graph, the matrix of it is a Boolean, Boolean matrix. Boolean matrix means it only has zeros and ones. Again, if you don't have more than one edge between any 2 vertices, parallel edges, then the only thing you have is either 0 edges or 1 edges. Okay, 0, 1. That's a Boolean matrix. A Boolean matrix is a matrix with only zeros and ones. So you wouldn't have had those 3s, 4s, 2s. Okay, you could only have zeros and ones. Okay, so plane graphs, this has 3 things, this has 2 things, this has 2 things. Plane graphs without those parallel edges correspond to what's called Boolean matrices, matrices with just 0, 1. That is the end of section 3.3. You have nice homework for it. Very nice. Now, we move on to chapter 2. We take a break. We'll come back, I promise you, to section 3.5. But there's one other operation that's not dealt with. The book in previous editions had this operation done in this section, okay? But in the 5th edition, for some odd reason, they felt it wasn't important. They took this operation called matrix multiplication and they put it in chapter 11. But matrix multiplication shows up in every single class in computer science. You'll see it in computer graphics. You'll see it in algorithms for sure. You'll see it in every single computer class, and I don't know why they took it out. It is extremely fundamental. It's another operation, and let's see how it's done. Okay. Okay, so let me first show you what's not done. Okay, so I'm sorry, this is section 11.3. Multiplication of matrix. Let me tell you what's not done. Okay, so you might say, oh, matrix multiplication, that's not hard. Well, cool, we'll take 3, 5, 7, 6, 0, 8, and we'll multiply it by 2, 0, 6, I don't want to multiply 6 times 7, I'll do 5, minus 1, 3, 2, okay? 2n by 2, this is a 3 by 2 matrix, this is a 3 by 2 matrix, and you'll say to yourself, I'm going to get out a 3 by 2 matrix, okay, and we're going to do it, what are the entries? Well, 3 times 2, 6, 5 times 0, 0, 7 times 5, 35, 6 times minus 1, minus 6, 0 times 3, 0, 8 times 2, 16. Okay? Now that seems like a typical or intelligent or sane operation. Okay? The problem is, that's not what matrix multiplication is all about. That is absolutely not what multiplication is all about. That's what you would think it is, but it's absolutely not that. And I'll tell you something even more. I've never seen this operation being used at all. So you can make it up if you want. It just doesn't show up. It's not. I told you, matrices and matrix multiplication not only shows up in every class in computer science, but in every class in physics, in every class in mathematics. Okay? But this operation, never seen it. Okay, so let me show you what is matrix multiplication. That is not matrix multiplication. Okay. The books are falling. Okay, I'm going to do an example first. By the way, this is Camus, The Plague. While we're living through the coronavirus, I strongly recommend that you read this book. It's a very good book. makes things understandable. So let me show you what it is. But first I want to show you an example of it. Okay? It's a lot more complicated than any of the other operations we had, but we're going to do it. Let's do a nice example. Okay? 6, 0, 4, 2, 0, 8. This is a 3 by 2 matrix. Great. Now I'm going to take a 2 by 4 matrix. Okay, 1, 0, 2, 9, 5, 5, 0, minus 8. Okay, and we're going to multiply them out. Now, you might say, hey, that's not right. They're not the same size. Good. I don't care that they're not the same size. What I do care is the following, and this is fundamental. This is important. What I do care is that these two numbers are the same. Okay. Once those two numbers are the same, that means I can multiply them out. Let me tell you what you're going to get in the end. You're going to get what's called a 3 by 4 matrix. So this is going to be 3 down and 4 across. In other words, 3 by 2, 2 by 4, the two numbers are the same, they go away, and you're left with a 3 by 4 matrix. 3 by 4 matrix. Great. I will tell you the secret formula of how to fill it in a second, but right now I want to just work it out and show you how to do it. You need 3 hands to do this. Okay? And it goes as follows. I want to figure out what the first position is. This is the first row, first column. So what I do is I look at the first row, first column, okay, and I fly these across. I fly these numbers across. Notice this has 2 elements, this has 2 elements. Why? Because there are 2 columns here and there are 2 rows here, so they're the same. And so we're going to bring them across, and we're going to do as follows. 6 times 1 plus 0 times 5. 6 times 1 plus 0 times 5 is 6. Okay? That is the first entry. Okay? Now, there's a second entry. We'll do that in a second. Let's do the third entry. Okay? So, this is the first row, third column. First row, third column. We're going to fly these across. Let's do it. 6 times 2 is 12, plus 0 times 0 is 0. 12 plus 0 is 12. Okay? Great. Let's do the fourth entry. Okay? Again, it's a little bit silly because of the 0 here, but 9 times fourth entry, right here, fourth entry. First row, fourth column, first row, fourth column. Let's fly them across. You get 9 times 6 is 54. 54 plus 0 times negative 8 is 0, so this is 54. Great. Now, let's go here. Let's keep an eye on what we're doing here. Let's keep an eye on what we're doing. I want to fill in the element, which is the second row, first column. Okay, and so I take the second row here, the first column here, and I fill it, and I fly this over here. So I get 4 times 1. 4 times 1 is 4, plus 2 times 5 is 10. So 4 times 1 plus 2 times 5 is 14. Okay, I'm sorry I skipped this one. Let's not skip this one. So let's do this. This is the first row, second column. First row, second column. 0 times 6 plus 5 times 0, 0. Okay, I'll do 2 or 3 more. Let's do this one. Okay, this is the second row, third column. So I'm going to look at the second row, third column. 2 times 4 is 8. 0 times 2, that's an 8. Okay? Now, stop. Stop the computer. Stop the YouTube. Stop it. Fill in the last elements. You have 1, 2, 3, 4. Fill in these guys. Because you have to get this at your fingertips. You have to know this operation at your fingertips. Okay? Let's fill it in. And we fill it in. I'm just going to read it. I'm going to just put it in. I did it myself. So you stop. Try to do it yourself. At the end, come back. And you'll see, hopefully, I'm right. 10, 8. This is 20. this is 40, this is 40, this is 0, this is minus 64. Okay, let's just make sure this 20, I'm a little hesitant about this 20. Let's see, this is the second row, fourth column, so we look at the second row, fourth column. 4 times 9, 4 times 9 is 36. 36 minus 16, 36 plus 2 times minus 8 is minus 16, and that's 20. So that's what we get. Okay, I'd like to show you now that we saw this example, I'd like to show you exactly how it goes. And it goes as follows. First of all, what is this matrix multiplication example? So this is, you take an m by n matrix, and you take a n by p matrix. Key point, don't even stop, key point, these two numbers have to be the same. Otherwise you can't multiply them. Okay? And what you get out from them is an m by the first and the third, m cross p. Okay? You get out an m by p matrix. Great. Now let me show you the formula that does it. Okay? I'm going to write the formula up on top because I don't want to bend. I'm getting old in my old age. Okay? Formula is as follows. You have a matrix A. You have a matrix B. You want to multiply them. You want to know what the ijth position of that matrix. I'm going to put parentheses around them so we can see it like that. A is a matrix. B is a matrix. A times B is a matrix. You want to know what the ijth position of that is. Well, let me tell you. Okay? Well, I'm going to look at okay. One to n, because they're going from 1 to n. Now remember what we said. This, the number of columns in this matrix is the same as the number of rows in this matrix. So what we're going to do is A times I, comma, K times B, K, comma, J. Okay. So what we do, what this does is it says, look, go through the number of columns here and the number of rows here. For each one of them, find the ith row here, the jth column here, and go through k of them. For each one of them, multiply out, add them all up, and put them in the right place. We'll do another example in a second, but you have to know how to do it. You have to understand this first. Okay? Notice we have an overloading of symbols here. Okay? Same thing as before. This is matrix multiplication. This is multiplication of real numbers. Okay? But fine, multiplying is multiplying. Okay? That's very nice. Okay? We're going to do 2 or 3 more examples, and we will be happy doing them. Great. Want to stop for a second? Okay, so I just wanted to go through these examples because these, well, any examples are important. Don't look at the answers. In all of them, I have 3 multiplications going on here. Don't look at the answers. Okay, so the first example is, let's just go through the dimensions. This is a 3 by 3. This is a 3 by 1. 3 rows, 1 column. Okay, they can be multiplied because they have the same 3, and what are you going to get out? A 3 by 1. Okay? Okay, and it works out. Let's just figure out how to do this. Multiply, you want to find out the first thing? Very good. Multiply this, 5 times 6 plus 0 times 0 plus minus 5 times 6, okay, is 0. Let's do the second one, so that's right 0. 5 times 0 plus 0 times 1 plus 6 times minus 2 is minus 12. 5 times 1 plus 0 times minus 1 plus 6 times 0 is 5. So you get that. Okay, I just wanted to show you, we're going to see, not we, but in the future computer science, any class you take, you're going to see a lot of things like this. For example, this, notice what's going on here. You have a matrix, and the matrix takes something and changes it into something else. Okay? What this is going to correspond to in computer graphics, in physics, in math, etc., in linear algebra, you're going to see this. In probability theory, you're going to see this. You can't do big data if you're not doing probability theory. You're going to see this over and over. What you have is, you have some type of state of the system, some type of thing. You're going to multiply it to describe the dynamics of the system, how the system changes. Okay? And you're going to get out something else, a different state of the system. So this goes up all over. It shows up in computer graphics. This is going to be some point. You're going to want to rotate the point. You want to move the point. You're going to want to rotate your view of the point, and you're going to see this. So many times you're going to have such a thing. Okay, this is just an interesting thing. Let's do the next example. This is, let's call this matrix A, call this matrix B. Okay, so this is a 3 by 3 matrix. This is a 3 by 3 matrix. Okay, and you get out, those two numbers match up, and so you get out a 3 by 3 matrix, and look what you get. Very nice. Now, these are what's called square matrices because the number of rows is equal to the number of columns. Well, you could also multiply them the other way because they're square. So you're going to have everything 3 here. Okay, so look what I did. I have A times B here, and I have B times A over here. Same thing. See, there's A, this is B, and I multiply them out. Now, I want you to don't look at these answers and actually work them out as a nice exercise. Work them out. But when you get them, you should see that these are the right answers. Okay? You should see that these are the right answers. And now you have to notice the following thing. They're not equal. They're not equal. So we have the following rule. In general, A times B is not necessarily equal to B times A. Now, this is a little upsetting because if you remember, I told you that matrices are essentially generalized numbers, and so with numbers, multiplication, you have that thing. But we don't care. We don't care. Sorry, maybe it's not clear enough, so I'm going to bring it up a little bit. Let's get it a little bit more clear. So we don't care that it's this is a fundamental fact about matrices. They're not necessarily commutative. Okay? Matrix multiplication. Now, this has tremendous significance in computer graphics, and quantum mechanics is based on this whole concept. The whole strangeness of quantum mechanics can be seen as a consequence of this thing. Okay? And if you're going to learn quantum computing, you better know that. Okay, next. However, this fact is true. Okay? It is associative. Matrix multiplication is associative. So that's a nice little fact, and we have to do it. Great. Let me just tell you a typical test question that you're going to have. A typical test question will be something like that. C transpose plus 3b, that's scalar multiplication, times 5a transpose plus 7 times d. Okay? I'll give you A, B, C, D, and I'll ask you to work it out. Now, how do you do it? Very simple. You do it from the inside out. Okay? As always with all math, you always work on the inside out. So figure out what CT is, figure out what 3B is, then add them together. Figure out what A transpose is, figure out what 5 times A transpose is, figure out what 7 times D is, 7 scalar multiplication, add them together. I'll make sure that they're the right dimensions, otherwise you won't be able to multiply them out, and you'll have it. Again, I promise you such a question on your midterm, on the final, on the next quiz, for a very simple reason. It's easy to make up such a question. Okay? It's also very easy to check the answer. I take the 3 smartest people in the class, see what they got. If they agree on all the answers, I assume that they're doing it. Anyways, but it's It's a skill that you have to know how to do, and so we'll do that. Okay? Let me show you something else. Let's look at a squared. Okay. A squared is equal to a times a. Okay. Let's take a look at a little typical example of that. Okay. Typical example of that is the following. 6, 0, minus 5, 0, 1, minus 2, 1, minus 1, 0. Multiply it by itself, or multiplying it by itself, is 6, 0, minus 5, 0, 1, minus 2, 1, minus 1, 0. Equals, stop the video, stop the YouTube, multiply them out. Okay? Start it again when you finish. Okay? I'm going to put up the answer, but I'm not going to go through the answer because we've done it already. This is 31, 5, minus 30, minus 2, 3, minus 2, 6, minus 1. And let's just work this one out just for the hell of it, just to work that out. So let's go through this. This is the third row, third column. So we're going to look at the third row, third column. And let's multiply it out. 1 times minus 5 is negative 5, plus minus 1 times minus 2 is negative 5 plus positive 2. So that's negative 3 plus 0 times 0 is 0. So that's negative 3. Okay, that's very nice. Question. How about a to the third? Okay, let's figure that out. That's equal to a squared times a. It's also equal to a times a squared. It doesn't matter how you write it, but that's equal. Okay, so what I'm going to do is I'm going to leave this up to you to figure out. Okay, you know what a squared is. Right here is a squared. Multiply that by a, and I'll tell you what the answer is. But again, you're going to have to do it on your do it by yourself. So multiply this times this. That's a. A squared times a squared times a. Okay, and you can get out a to the third. Let me just tell you what the answer is. But again, I'm leaving it to you to do. So stop the videotape, do it yourself, and make sure that I got the right answer. Again, you have to have this skill at your fingertips, not in your brains, at your fingertips. 156, 35, minus 165, 14, 5, 4, 33, 2, minus 28. Okay, so that's a nice example. Okay, and that's fine. Okay, the book ends off the chapter with a very nice application of this. And again, I can't stress enough how much open up any physics textbook, any computer science textbooks, any graphics textbook, you'll see it's all about matrix multiplication. So this shows up all over, but they have a nice little application here, and I'd like to show you the application. Okay. We don't do their example. The book has another example, so you'll see it twice, but I would like to show you this one example. This one example. So, consider the following. So, an application of matrix multiplication. Okay. So consider the following graph. Vertex 1, vertex 2, vertex 3. Okay. And this has one arrow this way. This has one arrow this way. And this has three arrows this way. 1, 2, 3. This has one arrow to itself. And this has one arrow down. One arrow up. Okay? Okay, now that is a directed graph with 3 vertices and 3 vertices. The matrix that corresponds to that is, you can almost count it, from 1 to 2 is 1, from 1 to 1 is 0, from 1 to 2 is 1, from 1 to 3 is 3, okay? From 2 to 1 is 1, from 2 to 2 is 0, and from 2 to 3 is 0. Great. Okay, and let me just, this is 0, 1, 1. So that's your matrix. Very good. Okay, I like to write up what this matrix is. The entries are, I did this 10 minutes ago, but it's worth doing it again. Mij is equal to the number of arrows from vertex I to vertex j. I'm going to write it another way. Number of paths of length 1. What's a path of length 1? It's an arrow. It's a single arrow. From vertex VI to from, we don't need vertex, we don't need the word vertex, we know it's from VI to BJ. Sounds good? Nothing shocking there. That's exactly what we did before. The last thing we showed was a directed graph can be written as a matrix. Great. Let's ask the following question. Let's erase this because we know what it is. Okay. No, let's not erase it. No, let's erase it. Okay. And let's look at M dot M. Matrix multiplication. Okay. I worked it out. All right, you know what? But we're going to write it out. 0, 1, 3, 1, 0, 0, 0, 1, 1. Close. Open. 0, 1, 3, 1, 0, 0, 0, 1, 1. Okay? And that should equal to, not it should equal, it does equal to the following. 1, 3, 3. 0, 1, 3. 1, 1, 1. Okay? But let's call this matrix M squared. Okay? But I would like to go through this number. Okay? So let's write, what is this number? Why is that a 3? Let's go through it. Okay? M squared of, this is the first position, second column. So this is 1, 2. Okay? Let's see what it's equal to. Okay? I'm going to look at first row, second column, and it's equal to 1 times 0 plus. Sorry. Let's write that over. You know what? I don't want to do that one. Okay, let's do that one. We're doing that one. Okay, let's do it. So it's 0 times 1. That's this guy times this guy. Plus 1 times 0. 1 times 0. Plus 1 times 3. I'm sorry, 3 plus 3 times 1. Okay? Okay, now this is 0, this is 0, this is 3. So that's equal to 3. That's why I put a 3 there. But I'd like to look at it another way. I want to look at it as follows. I want to go from the 1, 2 position. Question, how many paths are there of length 2 to go here? And the answer is as follows. Okay, look, how do you get to 2? Well, one thing you can do is go around 1 by itself and then go across like that. But there is no path to go around 1. That says there's no path to go around 1 times 1, so there's nothing there. Next, another thing I could do is I can go to vertex 2. Again, I want to go from 1 to 2 in a path of length 2. So I can go to vertex 2, and then I can go around here in some loop here. That would be my second leg of the journey. Okay? But there is no little path over here. So that's 1 times 0. So there is nothing there. Okay, the only way I can go to vertex 2, okay, is like this. Go here and then go up. Now, how many different paths are there of going here and then going up? And the answer is there are 3 ways of going down here and then 1 way of going down here. So it's 3 times 1. So there are 3 paths from here to here of length 2. Okay? So basically you add them together. Let me show you what M3 looks like. Okay? You're going to calculate it yourself, but it's worth multiplying it out. This is 3, 4, 6. 1, 3, 3. 1, 2, 4. I'd like to show you where that 6 comes from. Basically, this is going to correspond to, there are 6 paths from vertex 1 to vertex 3. Oh, I'm sorry, there are 6 paths of length 3. That's the 3 from the first vertex to the third vertex. So let's go through this. Let's see if we can find 6 paths from here to here. Okay, so it's not hard. You ready? 3 times 1 times 1. Sorry. Okay, let's be a little bit careful. Okay. Anyways, 3 times 1 times 1. That's 3 paths. And then what else can we do? Watch this. 1, 2, and then there are 3 of these. Okay. So I have 1 way of going here, 1 way of going there, and then 3 ways of going here. So that's another 3. That gives you the 6 things. Great. So let me show you what the definition of what this really is, and then I'm going to draw a picture for you to show you what's really going on. Okay, and it goes as follows. MK. Okay, I can multiply the matrix M by itself k times. If you look at the ijth position of that, you get out as follows. This is the number of paths of length k from vertex I to, let's not use the word vertex, too big, from VI to VJ. Okay? Now we saw this when I had a 1 there. When we had just a matrix by itself, we had a path of length 1. Path of length 1 is just an arrow. But here we generalized it and we talked about paths of length k. So you can actually figure out how many paths there are, okay, from one vertex to another vertex by multiplying it out. We will see this later when you do analysis of algorithms, and you'll see this in many other places, including, by the way, quantum computing. This shows up also. Okay, if you don't believe me, look at chapter 3 of my book. But this is a very fundamental notion of doing it. I'd like to explain it another way with a beautiful little picture that makes it all very understandable, if I can find a picture. Okay, I'm losing my mind. That's not a great thing. Here we go. Sorry. Okay, losing my mind. Okay, I want to explain to you how this works. Okay, I'd like to explain it to you just for M2. So, erase. I can erase, you have to recopy. Okay, and it goes as follows. I want to go from VI, here's vertex VI, to VJ. Here's vertex VJ. Okay, and I want to do it in things of 2. So, here's the possibility. This is vertex 1. This is vertex 2. This is vertex 3. This is vertex 4. Dot, 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 dot. This is vertex n. Okay? And I ask the following question. How many paths are there of length 2 from this guy to this guy? Okay? And the answer is very simple. Okay? Look at how many paths there are here. Look how many paths there are here. Okay? Or look at how many paths there are here. All right, let's make it simple. Just say this is one path from V1 to V2. Okay? And there's two paths from V2 to Vj. And look how many paths there are from here. Let's say there are k, let's not use the word k. Let's say there are 3 paths. And let's say there are 5 paths from here to here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And there's 2 paths from here. Okay, great. Now I want to add them all up. I want to add up how many paths there are from here to there. So look what I do. Okay, it's basically I have 3 ways of getting from here to here and 3 ways to getting from here to there, so that's 9. Okay, and then I have 1 way of getting there and 2 ways of getting there, so that's 2. But it's plus. Then I have 3 ways of getting from here to there, and then I didn't even draw in how many ways there are. And here there's 5 ways of getting from here to there and 2 ways of getting from here to there. That makes 10 ways going through that. Okay? And so I'd like to show you now, so we're adding up all these numbers because each way we can go here or here or here or here or here or here or here. Okay? And I'd like to add up all these numbers, and basically what we're doing as follows. M squared of the ijth position is equal to, let's write it out. Okay, it's equal to, it's m, the I times 1, I comma 1, times m 1 comma j, plus m I comma 2 times m 2 comma j, plus m, that's this times this, m I comma 3 times, that's how many ways of going from I to 3, times m from 3 to j, plus m I to n times m from n to j. N to j. Okay? Where did you see this before? This is exactly the definition of m times m, the ijth position. So this is just a graph way of explaining where the definition of matrix multiplication came from. This is exactly the graph way of explaining where the matrix multiplication. So I started off talking about matrix multiplication saying, you know, we could multiply it like that, the simple way, but I said that never shows up. Here you can see where it exactly shows up. Okay? The number of paths from here to here of length 2 is equal to, that's describing that thing. Okay? I just want to warn you, on the test I can easily ask you for M4. Okay? Now there are 2 ways of doing this. Let me just show you. You could take M, multiply it by M, that's one matrix multiplication, get the answer, multiply it by M, that's another matrix multiplication, multiply it by M, that's another matrix multiplication. So you did 3 multiplications altogether. Let me just show you another way of doing it. What you could do is take M, multiply by M, you get that. You get M squared. That's great. Now take the result of that and multiply it by itself again. You have that again. Okay, so, okay, that, so you do another multiplication, 2 multiplications, and you get M4. Okay, so again, you don't have to do 3 multiplications, you can do it in 2 multiplications. And guess what? If I asked you for M8, it's very simple. It's M4 times M4. So you just have to do 1 more multiplication, you get M8. Okay, so that's a very pretty quick way of doing things. Okay, so that is matrices. It's a very, very nice field. It shows up all over. It's very, very important in every single aspect of computer science, physics, and mathematics. Okay, so that's very nice. Next class, we're going to go section 3.4, which is called Equivalence Relations. We're going to go back to relations. Again, let's start over chapter 3. We talked about relations, we talked about properties of relations, then we took a little sidebar and spoke about graphs, okay? Figured out a lot of things about graphs. Then while we were talking about graphs, we might as well also talk about matrices. And we spent a lot of time talking about the different operations of matrices. Again, this class is a prerequisite for so many other classes because we have all these things. And it's very important. Take care.